Let us now start the discussion on module 3 of chapter 7. Now, in the first module of chapter 7, recall that we have defined a special type of functions called function of bounded variation. While examining the continuity properties of these functions, we have seen that if f is a function of bounded variation on closed interval a b, it need not be continuous. Similarly, if f is a continuous function on closed interval a b, then it need not be a function of bounded variation. Also, we have proved that f is a function of bounded variation if and only if it can be expressed as the difference of two monotonically increasing functions. Now, we know that a monotonically increasing function can have at most countable number of discontinuities. So, a function of bounded variation can also have at most countable number of discontinuities, but still it is not continuous. So, in this module we are going to present a much more stronger notion, an absolutely continuous function. We will see that this is the concept of a function which is both a function of bounded variation as well as it has very strong continuity properties. So, let us go to the formal definition of an absolutely continuous function in our first slide. A function f is said to be absolutely continuous on closed interval a b if for any given epsilon greater than 0 there is a delta greater than 0 such that sigma I is equal to 1 to n mod f di minus f ci, this is less than epsilon whenever we take a finite collection of non-overlapping intervals closed C I d I 1 less or equal to I less or equal to n in closed interval a b with the property that sigma I equal to 1 to n d I minus C I, this sum is less than delta. Obviously, from the definition of absolute continuity, it follows that an absolutely continuous function is uniformly continuous. So, we have seen from the definition that an absolutely continuous function is always uniformly continuous. The observation is very easy. Now, the question is whether the converse is true. We will see that the converse is not true. Consider the function f defined on closed interval 0 1, where f x is x sin pi by x when x is not equal to 0 and takes the value 0 at x equal to 0. Now, clearly f is a bounded function, and in the undergraduate level you have already seen that this function is uniformly continuous on closed interval 0 1. Now, we will show that this is not absolutely continuous. For that, what we do is that for any positive integer k, let us choose the points c k and d k in this way. C k equal to 2 by 4 k plus 1 and d k equal to 2 by 4 k. So, we have for each k a closed interval Ck dk. Now, observe that the series sigma k equal to 1 to infinity Ck is divergent, and so we can choose two positive integers capital K and capital L belonging to n, where capital K is less than capital L, such that this sum small k equal to capital L Ck, this is greater than 1. So, it follows from the definition of a divergent sequence of positive real numbers. We also choose the positive integer k in such a way that given delta greater than 0, this 1 by capital K is simultaneously less than delta. Now, consider this collection of intervals closed C I d I, where capital K less or equal to I less or equal to capital L. So, this is a finite collection of non-overlapping intervals in closed 0 1, and also we have that the sum of the lengths of the intervals sigma small k equal to capital K to capital L d I minus C I, this is less than delta. But see that sigma k equal to capital K to capital L mod f d k minus f c k, this is actually mod c k. So, this is greater than 1. So, this shows that the function is not absolutely continuous. Now, we prove that if f is absolutely continuous on closed interval a b, then f is also a function of bounded variation on closed interval a b. So, let us assume that f is absolutely continuous on closed interval a b. From the definition of absolute continuity, for a fixed epsilon, say epsilon equal to 1, there is a delta greater than 0, such that sigma I equal to 1 to n mod f d I minus f c I, this is less than epsilon whenever C I d I, where I runs from 1 to n, is a finite collection of non-overlapping intervals in closed a b with the property that the sum of the lengths of the intervals is less than delta. Now, choose a positive integer capital N such that b minus a by capital N is less than the given delta. Choose a partition P in this way: a equal to x 0 less than x 1 less than x 2 less than x n equal to b, where each point is at a equal distance from the preceding point, and the distance is b minus a by capital N, that is x r is equal to a plus r into b minus a by capital N. Then we have V a b f, that is the total variation of f on the whole interval a b. This is equal to sigma I equal to 1 to capital N V x I minus 1 to x I f, and this is less or equal to sigma I equal to 1 to capital N 1 since each variation is less or equal to 1 and the sum on the right hand side is capital N, which is a fixed positive integer, and this shows that f is of function of bounded variation on closed interval a b. Converse is obviously not true, as we have seen that step functions are functions of bounded variations, monotonic functions which are not continuous, that are also functions of bounded variations, but these functions are not absolutely continuous because they are not even continuous. Now, we prove an interesting result by showing that if for an absolutely continuous function f from closed interval a b to r, the derivative of f is equal to 0 almost everywhere in closed interval a b, then f must be constant on closed interval a b. So, in order to show that f is constant on closed interval a b, what we will show that for every point c belonging to open a b closed, f c is equal to f a. So, take any arbitrary point c belonging to open a b closed. Consider the set capital A as the collection of all those points x, where a less than x less than c and f dash x is equal to 0. Now, let epsilon and theta both arbitrarily small numbers be given. So, we start the proof in this way. Since f is absolutely continuous, so given epsilon greater than 0, we can find a delta greater than 0 such that whenever we take a finite collection of non-overlapping intervals c I d I in a b such that the sum of the lengths d I minus c I is less than delta, we have sigma I equal to 1 to k mod f d I minus f c I less than epsilon. Now, from the definition of derivative, observe that f dash x is equal to limit h tends to 0 f y minus f x by y minus x, y is equal to x plus h. So, in other words, f dash x is equal to limit y tends to x f y minus f x by y minus x. So, if at any point x f dash x is equal to 0, then mod f y minus f x by y minus x can be made less than any arbitrary small number. So, now set capital U as the collection of all closed intervals x y, where x less than y less than c and the points y and x are related by the property that mod f y minus f x by y minus x is less than theta, and U is the union of all these closed intervals. Now, it is easy to verify that these closed intervals cover the whole interval in the sense of Vitali. Now, using the Vitali covering theorem, we can find a finite collection of mutually disjoint closed intervals from this collection U, say x r y r, where r runs from 1 to capital N, such that measure of the difference, that is A minus union r equal to 1 to capital N x r y r, this is less than delta. We may further assume that the intervals are written in the increasing order, that is we have A less than x 1 less than y 1 less than x 2 less than y 2 less than dot dot dot. So, less than x capital N minus 1 less than y n minus 1 less than x capital N less than y capital N less than c. Now, measure of open interval A c minus A, this is equal to 0, and this implies that measure of open interval A c minus union r equal to 1 to capital N closed x r y r, this is less than delta from the above equation. So, in this case we have mu of open interval A c minus union r equal to 1 to capital N closed x r minus y r, and the sum can be written again as x 1 minus A plus sigma r is equal to 2 to capital N x r minus y r minus 1 plus c minus y capital N. And subsequently we have mod f c minus f a, this is less or equal to sigma r equal to 1 to capital N mod f y r minus f x r plus f x 1 minus f a mod plus sigma r equal to 2 to capital N mod f x r minus f y r minus 1 plus mod f c minus f y n, and the whole sum is less than theta into sigma r equal to 1 to capital N y r minus x r plus epsilon. And so, this is less or equal to theta into c minus a plus epsilon, because recall that the intervals x r y r are non-overlapping and they are contained in the interval a to c. So, the sum of their lengths is definitely less than c minus a. Now, as this is true for any arbitrary epsilon and theta greater than 0, however small they may be. So, we must have mod f c minus f a equal to 0, that is f c should be equal to f a, and this completes the proof of the theorem. Now, let us again see an interesting observation. We know that if f is a function of bounded variation, then it can be decomposed as the difference of two increasing functions. If the original function is absolutely continuous, then the components f 1 and f 2 are also absolutely continuous. So, given epsilon greater than 0 by the definition of absolute continuity, there exists a delta greater than 0 such that sigma k equal to 1 to n mod f b k minus f a k less than epsilon for every n disjoint open subintervals open a k b k of closed interval a b, where n belongs to capital N, and when the subintervals are so chosen that the sum of their lengths sigma k equal to 1 to n b k minus a k is less than delta. Now, partitioning each open interval a k b k into subintervals with the points a k is equal to say s k 0 less than s k 1 less than s k j k, which is equal to b k, we get sigma k equal to 1 to n, sigma j equal to 0 to j k minus 1, s k j plus 1 minus s k j, and this whole sum is equal to sigma k equal to 1 to n b k minus a k, and this is by definition less than delta. And consequently, sigma k equal to 1 to n, sigma j equal to 0 to j k minus 1, f s k j plus 1 minus f s k j, this is less or equal to sigma k equal to 1 to n, sigma j equal to 0 to j k minus 1 mod f s k j plus 1 minus f s k j, and this is less than epsilon, and we know that f is equal to f 1 plus f 2, and consequently we have sigma k equal to 1 to n f 1 plus f 2 of b k minus f 1 plus f 2 of a k less or equal to sigma k equal to 1 to n, sigma j equal to 0 to j k minus 1 mod f s k j plus 1 minus f s k j, and this is less than epsilon. Now, taking supremum over all such partitions corresponding to each subinterval a k b k, we finally get that sigma k equal to 1 to n mod f 1 plus f 2 b k minus f 1 plus f 2 a k, this is less or equal to epsilon, and this shows consequently that both f 1 and f 2 must be absolutely continuous. So, let us summarize what we did in this module. We have defined a very strong type of continuous functions, which is called absolutely continuous functions. It is stronger than uniformly continuous function, and as well as it is a function of bounded variation. And we have seen some basic properties of these absolutely continuous functions. And in the next module, we will continue to investigate these functions, and will show that these functions carry measurable sets into measurable sets. And with this comment, we end this module.